Okay, so this is lecture 23, and today is May 26, 21. So let's first finish where we stopped last time, and that was um, showing you how you use Lagrangian energy method to solve for the equation of motion. And this is the problem we had. We had a 2-degree of freedom system, this mass 1. We had a pendulum with mass 2 connected to that. This mass was moving in this direction, and the pendulum was rotating. So we had 2 degrees of freedom. And then we set up the equation, we set up the kinetic energy and potential energy. So let me rewrite those because we need them. 1/2 m1 u1 dot squared plus 1/2 m2 times u1 dot squared plus L squared u2 dot squared plus 2L u1 dot squared u2 dot cosine u2. This was kinetic energy, and potential energy was 1/2 K u1 squared plus m2GL times 1 minus cosine u2. So this is kinetic and potential energy. And to set up the equations of motion, you just follow this simple procedure. You see, you need to set this equation, okay, for each degree of freedom. And what is QI? In this case, Q1 is U1, Q2 is U2. So what you need to do, find these terms. First, you will take partial derivative of L with respect to each displacement term. In other words, you do this. You evaluate these two. So this part of this equation. What is the partial derivative of L with respect to U1? That means you subtract, of course, this from that. So I don't want to rewrite that. L minus, T minus V would be basically that minus this. So you end up with negative here, negative term here, right? That's what it becomes, L minus V. So partial derivative with respect to U1, meaning that U1 is the only variable. Everything else is a constant. You don't have U1 here. You only have U1 here, and that's it, right? So partial derivative of this quantity with respect to U1 would be only the, for this term, and that comes out to be negative K times U1.
Professor,
Yes.
why wouldn't you have to derive the U dot one terms? Or do the
No,
derivative?
you do each of these separately. So what I'm setting up all the elements in this equation.
Oh, that makes sense. Thank you.
Yeah, and then I'll do that later. Thanks for asking that question. So I started with this first. So now the second one would be taking the derivative with respect to U2. In other words, U2 is the only variable. You have no U2 here. You have no U2 here. You only have U2 here. So if you take that derivative, would be what? It would be simply what would be minus M2, right? GL constant times the derivative of this, which would be U2 times the cosine of U2, okay? I'm sorry, a sine of U2. So you see, the only U2 term, oh, I'm sorry, you have also this term here, U2. So you will have minus M2, okay? And I think I'm missing 1/2 here. So you have minus M2 times L. Everything is constant. You see, minus L, U1 dot, U2 dot, these are constant, and times derivative of this, which is sine.
Professor, would you mind shifting your page up?
Oh, sorry about that.
Thank
Sorry
you.
about that. Sine U2 minus this one, which would be M2 G L sine U2. So you have only this derivative and derivative of this term, which becomes this. Okay. Now, assuming that U2 is very small value, sine of U2 is almost U2. So this is almost U2. However, if U2 is small, all quadratic terms, product of U dots will almost be zero, would be very, very small. The product of two very, very small number would be a very small number. So we can ignore this term. So this can be simplified just being minus M2GL U2. So this is the partial derivative with respect to the two displacement terms. Now you need to take the partial derivative with respect to the two velocity terms. Partial derivative with respect to U dot 1 and U dot 2. So again, you look here, the only thing is the variables is U1 dot. So this and here, this term, you don't have U1 dot here. So if you take the derivative, assuming that U1, in other words, consider that U1 dot is X, okay? So you have 1/2 M1 X squared. So it would be 2 times 1/2 times M1 X, right? So if you take that, you get M1 U1 dot plus M2 U1 dot, okay, for this term, and then this term, which becomes plus M2 L U2 dot cosine of U2, okay? And again, if U2 is small, this is equal to 1, so this would be simplified as M1 plus M2 times U1 dot plus M2 L U2 dot. So that's that velocity term, okay? Now, for this one, you consider only, and I let me see, I hope, let me raise this so that everything will fit in one page. That's better. So now in this equation, you consider T minus V, you consider only taking the derivative with respect to U2 dot. There's no U2 dot here, no U2 dot here, nothing here. It's only these two terms. If you take that derivative, assuming U2 dot is the X, you get M2L squared U2 dot, okay, plus M2L U1 cosine of U2. Again, U2 being small, this simplifies as M2 L squared U2 dot plus M2 L U1 dot. Now you set up, now you have these terms, all you need to do, take the derivative, this is what you need to do, with respect to time of the partial derivative with respect to U1 dot minus partial derivative with respect to U1, okay? That gives you the first equation of motion, and then partial derivative, the time derivative of that partial derivative with respect to U2 dot minus partial derivative with respect to U2 is equal to 0. So all you need to do, take the time derivative of this, subtract this one from it. In other words, if I call this 1, 2, this is 1 prime, this is 2 prime, you just take partial derivative of 1 prime, take the time derivative of 1 prime, subtract 1 from it. So that's all I do. Take the time derivative of this, it simply becomes M1 plus M2 U1 double dot plus M2 L U2 double dot. So that is this, okay? Then subtract that, which would be plus K U1. So that's the first equation of motion. You do the same thing here. Take the time derivative of this, would be M2 L squared U2 double dot plus M2 L U1 double dot. So this is this term minus this. So it becomes M2 G L U2 is equal to 0. So this is the equation of motion corresponding to this 2 degree of freedom system. If you wanted to use second law of mechanics or setting up free body diagram and so on to find this equation of motion, it would have been just simply a nightmare, I can assure you. It would not have been easy at all to find that. Okay, any questions?
Does this equation or method only work for like a system like not under like a harmonic or general force?
No, this applies to any conservative system. Doesn't matter. Any
Okay.
conservative system. You can use this to derive the equation of motion.
What exactly does conservative mean?
Meaning there is no damping in the system.
Okay. Okay, so no damping.
So in other words, you can assume that there's no energy dissipation in the system. Therefore, you can apply the concept of the conservation of energy. Okay. All right. So with that said, now let's see where we are. Okay. Oops, I was using the back of a scrap paper, piece of paper. All right. So let's see where we are. We have now introduced how to derive equation of motion, right? Using two approaches, either direct approach meaning mechanics, second law of mechanics approach, or energy method, Lagrangian. Now, similar to the case of single degree of freedom systems, if you recall that, okay, what did we do? We introduced the equation of motion. Then we said, okay, let's do this. We're going to look at two cases, free vibration and forced vibration. And in each case, we categorize to undamped and damped systems, okay? So we have four cases that we want to study, and we started with this free vibration of undamped systems. So let's do that in the case of 2 degree of freedom systems now. That means you have two masses, M1, M2, K1, K2. System is vibrating, and you want to find, this free vibration. In the case of single degree of freedom system, you see, this was the equation of motion. This was a homogeneous second order differential equations. So you assumed U would be of this form, okay? And you would basically substitute this back into the equation. You found the frequency, which was a natural frequency, and we solved for the two roots and so on. So we do exactly the same thing here. So since we have the equation of motion for this case would be of this form, M1. If you set up the equation of motion, this is what you have. K1 plus K2 times U1 minus K2 U2 is equal to 0. M2 U2 double dot minus K2 U1 plus K2 U2 is equal to 0. So we have this represent the free vibration of this 2 degree of freedom system, and we want to solve for the solution. So we do assume that U1 is also a harmonic, so of a harmonic form like this, similar to single degree of freedom system. And we need to substitute these, put them into this equation as we did here, in order to solve for the natural frequency first, and then for the amplitude, okay? So let's do that. If you substitute these two into that equation, what do I mean by that? You consider U1 double dot, which would become negative omega squared A1 sine omega t, U2, I need that. U2 double dot would be negative omega squared A2 sine omega t. So you substitute U1 and U2 and U2 double dot and U1 double dot in this equation. And if you simplify that, a little bit of algebra involves, do substitution and simplification, you end up with this equation, negative omega squared M1 plus K1 plus K2 times A1 minus K2 times A2 is equal to 0. And you end up with negative omega squared M2 plus K2 times A2 minus K2 A1 is equal to 0. Okay. So you have now a set of simultaneous homogeneous equations. Remember from your linear algebra or calculus, whatever, if you have a homogeneous set of simultaneous equations, in order for this set of equations to have a solution that is non-trivial, because the solution to this is obviously A1 and A2 equal to 0, satisfy this. But in order to have non-trivial solutions, use Cramer's rule, which told you eventually that the determinant of the coefficients of the unknowns has to be 0. Unknowns being A1 and A2. So you just take the coefficient of the unknowns, A1 and A2, set up that determinant. That determinant would be negative omega squared M1 plus K1 plus K2 minus K2 negative omega squared M2 plus K2. In other words, this is, if you write that simultaneous equation in terms of this matrix formulation, this is the determinant of the unknown coefficients. For this to have a non-trivial solution, this determinant has to be 0. How do you find this determinant? Easy. You remember 2 by 2 determinant. This times that minus this times that. That results, if you perform that operation, that would result in a quadratic equation, okay, where x is omega squared. So if you do that multiplication and simplify this, okay, you will get this equation. You will get an equation that looks like this. I don't want to go through all the details of the algebra, okay? So I will just set it up for you. You will get, okay, if you do that, okay, and you simplify, maybe I'll do that, I don't know. I mean, you can do that easily, right? What I'm saying, product of this times that minus this times that. You get the second order, you get the quadratic equation, and the roots of that equation, that means omega squared, 1 and 2 roots, can be easily found from this relationship. The quadratic equation, right? Minus b plus square root of b squared minus 4ac over 2a. If you apply that, this is what you get. K1 plus K2 divided by m plus K2 over m plus and minus square root of 1/4 K1 plus K2 divided by m plus K2, m1, over m2 squared minus K1, K2 over m1, m2. So these are the 2 roots that you can find.
Professor, what are the subscripts under the 2 terms, K1 plus K2 over to the left? I'm pretty sure it's M1 and M2.
This one? I'm sorry. This. Sorry about this. Is M1 and M2. Sorry.
Okay, cool. Just want to check.
Sorry. So these two roots that correspond to those oscillatory motions for each degree of freedom are called, in other words, omega 1 and omega 2 are the natural frequencies. In the case of a single degree of freedom system, you had one omega, which was K over M, right? In this case, you have two omega. So as the system vibrates, okay, for the first frequency, the system would displace in certain way, and for the second frequency in a different way. We'll get to that. You know, for instance, if you have a 2 degree of freedom system being this cantilever beam, for the first frequency, system is going to vibrate like this. For the second frequency is going to vibrate like this. Each of these, this corresponds to omega 1, corresponds to omega 2. We call these mode shapes. We'll discuss these in a minute. So the situation in the case of multi-degree of freedom systems is not as straightforward as it was in this, single degree of freedom system. In order to solve the problem, there we were able to find both the frequency and the amplitude. Here we found the frequencies. Now we will see later, in a minute actually, how you can find those amplitudes. So let me demonstrate that through an example problem, because this equation obviously is nasty. So let's do some kind of a numerical problem, problem with some numerical values to demonstrate this, what we did. So I will use that same example of that building where this was W2, this was W1. The material and geometric characteristics of each column is given. Let's say, to make life easy, assume the two weights are equal. In other words, the two masses, M1 and M2, would be equal, or W over G. I1 is equal to 2i the I2. So let's normalize this. This is, let's say, 2i. L1 is twice the L2. And let's say this is L. And so K1, if you remember, was each K was 24 EI over L cubed. And if you, with these values, if you put in, you see that K2 would be K1 over 2. So we have these values, okay? And also, I will give you another quantity.
Professor, can you scoot up your page?
Oh, sorry about that. I always do that. Shame on me, right? Okay. So, so I also give you this value, which you will need if GEI over WL cubed, let's say that is 2. So with these numerical values, let's set up the equation of motion. I don't want to redo that because it's similar to what you had. But if you set it up and simplify that, you will get, for the equation of motion, you get something like this. You get, okay, something like this. What did I do with that? Here it is. You get U1 double dot plus 3BU1 minus BU2 is equal to 0. U2 double dot plus B U2 minus B U1 is equal to 0. These would be equations of motion where B is 12 EI G over WL cubed. So I set up the equation of motion, which is what you had before, this simply these, okay? And I had K1, K2, M1, M2 substituted and divided everything, the first term by, and second term by W, and that's what you end up with, okay? And of course, as I said, to simplify the problem, I set to be equal to 2. So you want to solve now these equations, and as we said, you cannot solve them. All you can do is you can take, since these are homogeneous equations, condition for the solution is that the determinant of the coefficients, which would be omega squared plus 3b minus b minus omega squared plus b, this has to be 0. If you set this equal to 0, you get this quadratic equation in terms of omega squared. Okay, 4b omega squared plus 2b squared is equal to 0. So if you solve for omega 1 and omega 2 squared, you get these values, 0.586 b and 3.414 b. Substitute for b, given this assumption that I've given, GEI over WL cubed is 2. If you do that, you will get omega 1 comes out to be 3.75 radians per second, and omega 2 would be 9.05 radians per second. So these are the frequencies. Now, I need to find the amplitudes of this oscillatory motion, right? So what do? Let's go back to the equation I had. This was the equation where you substitute for U1, A1 sine omega t and A2 sine omega t. This was the equation. You had negative omega squared plus 3b A1 minus b A2 is equal to 0.
Professor,
Yes?
could you slide down that earlier page a little bit?
Oh,
Cause
the earlier page.
I
this
didn't,
one?
yeah, I didn't get the end
Oh,
of
sure,
it.
no problem. So why don't I
Thank
do this? Okay, I do it like this. So
Also,
minus
the determinant, when you did minus omega squared plus something b, is that a 3?
3b, yes, correct, yes. Yes, it comes from here.
Okay.
Okay, so determinant of the coefficients. Okay, so now if you set this up, equation, you have this plus b minus omega squared times A2 is equal to 0. So you want to solve for A1 and A2. But as we said, this is a homogeneous equation. So you cannot find a unique solution for A1 and A2. The unique solution is only A1 and A2, both are 0. The non-trivial solutions, these are not independent equations. So all you can find is take either of the two equations, divide it by the other variable, and find the ratio of those two unknowns that you're looking for. So that's what we do. So what I will do, I will
Quick question.
consider, yes,
Can you briefly go over why you can't solve for these equations? Because I'm
See
looking
here-
here and I just see two
right.
equations, two unknowns.
If you
Am I
remember
missing
from
something?
calculus, when you have a homogeneous set of equations, okay, if I go back, something like this, you had a1x1 plus a2x2 is equal to 0, b1x1 plus b2x2 is equal to 0. The way you solve for x1 and x2 was x1 was you set up the on the would be this numerator divided by this denominator. Numerator is a1, b1, and the second column is this. The denominator is a1, okay, a2, b1, b2. So, and same thing for x2 would be a2, b2, 0, 0, and same thing, Cramer's rule. So you can see that solution to this equation, x1, x2 would be 0. The only way that these would be non-zero is what? That this would be also 0. So you have x1 is 0 over 0 and x2 is 0 over 0, which is indeterminate. So you use L'Hopital's rule in order to find that non-zero solution. So that's the only possibility that these would have non-zero solutions. But that rule requires that this determinant would be 0. That's why we say the determinant of the coefficients have to be 0 so that you get 0 over 0 non-trivial solution. Going back to linear algebra. So in this case, that's what we did. Determinant of the coefficient was 0, but we set that and we found omegas. Now, for this these two are are not independent. So you cannot solve for them. You can only solve for the ratio of these. That means I can only consider one of these equations. So I will only consider, say, the first one, which is a1 omega squared plus 3b a1 minus b a2 is equal to 0. And divide that by the other variable. In other words, a2 would be minus omega squared plus 3b divided by b times a1. And then, or a2 over a1 is negative omega squared plus 3b over b. I can only solve for the ratio of these variables because they're not independent. So what that means, I can find the qualitative value of these. That means if, let's say, for omega 1, which was omega 1 squared was 0.586b, if I set a1 equal to 1, a2 becomes 2.414 for omega 2 squared being 3.414b. If a1 is equal to 1, a2 is negative 0.414. So for each frequency, we can only find the qualitative value or qualitative shape of the deformed system. In other words, if this is for omega 1, if this mass moves 1 unit, the other mass would move 2.414 units. For omega 2, if this mass moves 1 unit, the other mass moves in the opposite direction, 0.414 units. We call these mode shapes. So for the free vibration of undamped 2 degree of freedom systems, we can find the natural frequencies and the corresponding qualitative shapes of deformation for each frequency, which we call them mode shapes. So this is mode shape 1, corresponding to frequency 1, or the fundamental frequency. This is mode shape 2, corresponding to second natural frequency. Any questions? We will see later on how you can actually find the solution to this problem, especially in the case of force vibration. How do you find the physical displacement U1 and U2? You cannot do it yet. That requires to transfer these equations into a different coordinate system. We'll talk about that. Find U1 and U2 there and find the displacement there, transform them back into this coordinate system. We call those moral coordinates. But for the time being, all we can do when you're given a 2 degree or a multi-degree of freedom system, you can find the natural frequencies corresponding to each degree of freedom and the qualitative shape of deformation corresponding to that frequency, which we call that mode shapes. With that said, I'm going to stop here and see you during my office hours or see you on Friday. But